Next, we are going to talk about planar graphs. And as the name implies, a graph is called planar if it can be drawn onto a two-dimensional plane without any edges crossing each other. Now look at these examples. These two are what we call complete graphs because every vertex has edges to every other vertex. And K4 is the complete graph with 4 vertices, and K5 is the complete graph with 5 vertices. Now, when you look at both of them, it looks like they are both non-planar graphs. But that is true only for K5 because you see, if you find an isomorphism, or rather an automorphism in this way, or simply if you redraw this in this way, you see now this is a planar graph. Therefore, K4, even if you can draw it like this, since there is a possibility to draw it in this way so that no edges overlap or cross each other, then this graph is planar. Now, algorithms for checking planarity linear in the number of vertices. So this is quite an efficient solution to this problem. And another important concept regarding planar graph is Euler's formula or Euler characteristic for planar graphs. This gives you the number of regions in a planar representation of a connected planar simple graph. You have E edges and V vertices, and the total number of areas or the regions that the two-dimensional plane is divided into is given by E minus V plus 2. Now, when you look at this, for instance, you have the outer region here, 1. You have this region here, 2. This region, 4. 3, and this region makes 4. Therefore, the Euler characteristic for K4 is 4. And when you look at the formula, E is the number of edges, and that is 1, 2, 3, 4, 5, 6. Number of vertices is 4, so minus 4. And you have plus 2. 6 minus 4 plus 2 gives you 4 as expected. Now, be careful about this. If you do it on this representation, 1, 2, 3, 4, 5. Why doesn't it work? Because you see number of regions in the planar representation. The planar representation. So you have to first draw it as a planar representation, so no edges cross like this. And then you count the regions. Now, the proof of this is by induction, and it's not really that difficult. Let me try to construct it for you. For instance, well, you have to start with the basis step. And this would be the simplest graph you can imagine with a single vertex. Now, E here is 0. V is 1. Therefore, the Euler characteristic is equal to E minus V plus 2, 1. And that is correct because you just have one region here. The entire plane, it's not divided at all. So it's correct for the basis step. And in the inductive step, you assume that you have this Euler characteristic formula satisfied for a graph with, let's say, the number of vertices with, let's say, K, V equals K. Let me put it here, inductive step. Let's say this formula is true for a graph with K vertices. Now, if you want to add a vertex, let's say you have a graph. Okay, you have a graph with K vertices, and the number of regions is given by E minus V plus 2. And of course, we assume the number of edges is E. When you add a vertex here, you will have to add an edge to that vertex, because you see this has to be a connected graph. So when you add a vertex, you also add an edge. Okay, so E increases by 1, V increases by 1, but you see when you add it like this, you don't have a new region, so it checks out because E minus V is the same. So this is induction through B. You should also do an induction through E because you have two parameters here. And in the inductive step, you again assume the given formula is satisfied for E equals K. And if you keep the number of vertices the same, but increment the number of edges by 1, now be careful here. You cannot, for instance, add an edge like this one, right? Therefore, you cannot really cross other edges. So what you add is something like this. Okay, so the number of regions increases by 1 through this addition. When you add an edge, the number of regions increases by 1 because you do not cross any other edges. So the increment in the number of regions is 1. And since you add an edge, you increases by 1. The number of vertices stay the same. Therefore, the Euler characteristics increases by 1 as expected. Okay, so that completes the proof. So Euler's formula for planar graphs is given by E minus V plus 2 as the number of regions in the planar representation.